Good day, viewers all over the world. We are still under ordinary differential equations, solutions to ordinary differential equations. So we have, in the last lecture or last class, we have defined, we have introduced how we can recognize linear differential equations if it is homogeneous or non-homogeneous. Today we want to look at linearly independent solution. That is, if you are given any differential equations, either the differential equation is homogeneous or non-homogeneous, how do we find the solution? How do we determine the solution to such linear differential equations? We move a set of functions y1 of x, y2 of x, up to yn of x is linearly dependent on the interval a to b, closed interval a to b. If there exists a constant c1 up to cn, not all zeros, such that c1 y1 of x plus c2 y2 of x plus up to cn y of n is equivalent to 0 on the interval. That is, when we have second order linear differential equations, this is how we normally write the solution. If all these constants, C1, C2, C3, if they are not all zeros, then this set of functions is called linearly dependent on this interval. That is, we have to note that if C1 is equal to C2 up to Cn is equal to 0, that is a set of all constants that always satisfy this equation 1. Okay, but we want to look at linearly independent solution. Then this is the condition for linearly independence. If the only solution to this function is C1, that is C1, C2, all the constants is equal to 0, then the set of this function, the set of the function y1, y2, y3 up to yn is linearly dependent on that interval. If all the constants are not 0, the sets of that function are called linearly dependent. But if the solution, all these constants, they are equal to 0, then the set of that function are called linearly independent. That is the difference between linearly dependent and linearly independent solution. When it comes to first order differential, when it comes to second order or nth order, let's say nth order linear differential equations, if all the constants are equal to 0, the set of functions which represents the solution to the second order or nth order differential equation are linearly independent. But if not all the constants are equal to 0, then the sets of functions which represent the solution to that nth order linear differential equations are linearly dependent. So there's this particular theorem that must be noted under the solution to nth order differential equations, and that's what I'm about to state now. Theorem. This theorem is very important. The theorem is very important when it comes to solution of nth order differential equation. Theorem. Let me call it theorem 1 or something. Theorem. So the nth order, the nth linear homogeneous differential equations, that is, when we say Ly equal to 0, always as n linearly independent. Always ask n linearly independent solutions. So we should take note that when we have the nth linear homogeneous equation, in case of homogeneous equation, the right hand side of that equation must be equal to 0. Then when we have linear homogeneous equation, We only have one solution to that. And that solution is called the complementary factor. But whenever the right hand side of a linear differential equation is not equal to 0, then there are two solutions that will be stick for. We are going to find the complementary factor. Thereafter, we go ahead and find the particular integral. But this theorem is telling us now that the nth linear homogeneous differential equation, that is, when the right hand side of that differential equation is equal to 0, always has n linearly independent solution. So let's take notes. It always has n linearly independent solution. That's what we're trying to say, is that if y1 of x, y2 of x, up to yn of x, if it represents this solution, that is the solution to homogeneous equation, then if this represents the solution, then the general solution of the nth order homogeneous linear homogeneous differential equation is this represents general solution. By the time we give example, we are going to understand better. The general solution will be C1 y1 of x plus C2 y2 of x plus plus Cn yn of x. So where C1, C2 are arbitrary constants. So this will represent the solution. This will be the solution of the homogeneous differential equation. So we are going to give example by the time we introduce second order linear differential equations. When it is homogeneous, this will represent the general solution. But when it is non-homogeneous, we go ahead and first find this will be the complementary factor. It represents the general solution when it's homogeneous. But when it is non-homogeneous, then by the time we find the complementary factor, we go ahead and find what is called the particular integral. Then the addition of the two will represent the general solution. But here we are talking about homogeneous equation. So let's take note that the nth linear homogeneous differential equation always has n linearly independent solutions. So let's take note. Thank you.